Let's look at another example. We've got saccharine, which is a sugar substitute. It's a weak acid with a pKa of 2.32. It ionizes an aqueous solution as follows. So we have our saccharine, and of course it's in water, so it dissociates into H+, or as we know, H3O+, and the conjugate base, which is the same minus that acidic hydrogen. So we want, what we need is the Ka, but we're given the pKa. So let's think about what we know about what that P is telling us. Think back to how would we find the pH of something? Well, the pH is the negative log of our H+, or our hydronium ion concentration. So if we had the pH, how do we get back to this? Because we need the Ka. And remember that Ka is, in this case, it would be our products, our H+ concentration times the NC7H4SO3 minus, so our dissociated ions over our molecular acid concentration H NC7H4SO3. We need this, we need the Ka. We're given the pKa. Similar to if I needed the pH, or I'm sorry, if I needed the H, how do I work backwards? Well, to get the H plus concentration, we would do 10 to the negative pH, right? We just need to do the opposite. So if I want the Ka and I have the pKa, it's going to be a similar setup where my Ka is equal to 10 to the negative pKa. So let's solve for this and do 10 to the negative 2.32. And let's get our calculator out. 10 to the negative 2.32. So now we have our Ka value of 0.004786. So Ka is equal to 0.004786. Now we can work backwards and we can do our ice table because we need to find the pH of a 0.1 molar solution of this substance. So, all right, so we have our ice table. Let's do this. We have our HNC7H4SO3 with water. I'm just going to leave it off in this case with our H plus or H3O plus if we would have included water. And then NC7H4SO3 minus. We have our conjugate acid or conjugate base, our dissociated versus our molecular non-dissociated. So let's set this up. Okay, we're given an initial 0.1 molar of our acid. And again, we know that we have no product as of yet. And we're all a 1-to-1 ratio, so I'm going to lose reactant and I'm going to gain product. So I have X, X, and 0.1 minus X. So let's set up and see if our 5% rule will work here so we can do the easy setup instead of doing our quadratic formula. So we have our products over reactants, and we're going to assume that we're not doing 0.1 minus X, right? We're going to assume that we have our very little 5% loss of our initial. So we're going to do our Ka, which is 0.004786. Ka is equal to our product, so X squared, over reactant, and again, we're going to do 0.1. And let's solve for X. So we're going to cross multiply here. We're going to do 0.004786 times 0.1. And then that's equal to x squared. So let's take the square root of our answer to get x. So we got x is equal to 0.02187. Let's go to that. X is equal to 0.02187. We'll go one more, 7. Now, let's double check to see if we followed the 5% rule. So we're going to check 5% rule. And remember, by doing that, we need to check our X, our hydrogen ion concentration, over our initial. So let's do this. Let's do our 0.021877 divided by 0.1. And then times it by 100. Okay, so we've got that. Now divide it by 0.1 and times it by 100. And ooh, we got 21.8, almost 22%. So can't do it. That's not following the 5% rule. We have to do the quadratic equation. So we're crossing this off. Back to the drawing board. We can't use this. We have to do our quadratic formula. So I'll get another piece of paper here. So back to the drawing board. We got to do our Ka 0.004786 is equal to x squared over, well, we got to include that 0.1 minus x. 0.1 minus x. All right, so let's cross multiply. So then I would have 0.1 minus x times our 0.004786 is equal to x squared. And again, I want to set it equal to 0, so I'm going to subtract minus x squared on the left. We'll distribute 0.004786 times 0.1. So I would have 4.786 times 10 to the negative 4 minus 0.004786x minus x squared. Let's write this a little bit neater. So minus, and then minus x squared. So I have my A. My A is -1. My B is -0.004786. And my C is 4.786 times 10 to the negative 4th. Let's plug this into our quadratic equation. So when I plug in my A of -1, my B -0.004786, and my C is 4.786 times 10 to the negative 4th. I get two values, and again, one value, it can't have the negative value. So I'm going to use my x is equal to 0.0196 molarity. And again, my x is equal to my H plus concentration. So to find my pH, I'm going to do the negative log of my H plus concentration. Negative log of 0.0196 to give me my pH. Let's type that in. Negative log of 0.0196. Should get a pH of 1.71. So just to review what we did, we started the pKa, I needed the Ka. So I did just what I would do if I needed the hydrogen ion concentration and I was given pH. I did 10 to the negative pH to get my hydrogen ion concentration. To get Ka from pKa, I did 10 to the negative pKa. So 10 to the negative 2.34. That gave me my Ka. Then I needed to do my ice chart. I was given 0.1 molar initial. So I knew that I had no product, I lost reactant, I gained product. So I had X, X, and 0.1 minus X. Well, we tried to save ourselves some work by assuming that we were under the 5%, so we could just use our initial concentration, assuming that there was very little of our original lost. But when we tried to do that, we got over 20%. So had to rule that out. We had to go back to the drawing board and plug our products, our X times X is X squared, over our reactant 0.1 minus X. We had to cross multiply. We had to get everything on one side so that we could use our quadratic equation. So we had to distribute this and subtract X squared to get our A, B, and C. We found the X that worked. We took the negative log of it to find its pH. All right, our second and our last problem for this little set that we're doing is looking at the percent ionization of hydrozoic acid, HN3, not to be confused with ammonia, which is NH3. That's a base. Hydrozoic acid, HN3. For each of the following concentrations. So we need to have that appendix D because we need to know the Ka for hydrozoic acid. So let's look that up first real quick. I'm going to scoot this over here. Hydrozoic acid, HN3, with a Ka of 1.9 times 10 to the negative fifth. Okay, so Ka is 1.9 times 10 to the negative fifth. So percent ionization, if you recall, is when, here we go, let's write it over here. Find percent ionization is taking our hydrogen ion concentration at equilibrium divided by our initial acid. So we'll say our HA, that's our INITIAL, initial, our initial acid. That'll give us our percent ionization. So we need to do our ice table, and for here we've got 3 different concentrations to see the percent ionization going from 0.4 down to 0.1 down to 0.04. So our concentration is becoming less and less. So let's see what our ionization is. So let's start here with our ice table. We've got hydrozoic acid, so HN3, and we know that it is combining with water, so we're going to have our H plus or H3O plus, depending on how you're writing it, and we're losing our H, so we just have N3 minus. I don't know why I put those brackets there. Oh well. Okay, so let's start with our initial, our change, and our equilibrium values. Again, we're starting with 0.400 molarity, no product. We know that we're adding X. We know that we're losing X. So here we've got X, X, and 0.4 minus X. Now, let's set up to find X. So we've got our Ka is equal to our products, X times X versus X squared over our reactants. Now, let's start off thinking that we've got our 5% rule. So let's leave off this minus X. We'll just cross this off for right now and hope for the best. Remember, if it's more than 5%, we'll just start it over and include that minus X and use our quadratic equation. So let's start with 1.9 times 10 to the negative fifth times 0.4 times 0.4. And then that would be equal to X squared. So let's take the square root of that. Ooh, what am I gonna do? Oh, all right, 1.9 times 10 to the negative fifth times 0.4. And then I want to take the square root of my answer. There we go. So I got X is equal to 0.00276. All right, now remember, to find our percent ionization, we need to do our x, which is our H plus, divided by our initial, which was 0.4. So let's hope that we get less than 5%. So if we do our answer, divide it by 0.4 and times it by 100, we get 0.69%. 0.69%, well below our 5%. So there we go, we'll take it. All right, let's see if this trend continues. So let's go down to letter B, where the only difference is my concentration has gone from 0.4 to 0.1. All right, so we're going to have the same ice chart. The only difference will be that this will be 0.1. So let's set up our same Ka, 1.9 times 10 to the negative fifth is equal to x squared over, instead of 0.4, we'll be using 0.1. So let's do this math. We'll do 1.9 times 10 to the negative fifth times 0.1, and then we're going to square root that. The answer, 0.001378. Let's say that. X is equal to 0.001378, which again is equal to our H plus. And we want to take that divided by my initial acid concentration. In this case is 0.1, and we'll times that by 100. So let's do this divided by 0.1, times it by 100. Oh, and we got 1.38%. Okay, we're doing good, 1.38% ionized. So 0.69, 1.38. Now let's try this next one. Again, we've got the same setup. We're just going to use 0.04 this time. So 1.9 times 10 to the negative fifth is equal to x squared over 0.04. Let's plug that in to find x. 1.9 times 10 to the negative fifth times 0.04, and then square root that answer. So we got 8.7177, let's write that down. X is equal to 8.71779 times 10 to the negative fourth, which is equal to our H plus concentration. Let's divide that by our 0.04 and times it by 100. Divided by 0.04 and times it by 100. Okay, we got 2.18%. So 2.18%, which is great. This problem allowed us to not use the quadratic equation. So this problem really allowed us to look at percent ionization. And remember, that's looking at our hydrogen ion concentration at equilibrium compared to my acid concentration initially. So part divided by whole and times it by 100 to get the percent. And again, if it's less than 5%, we can use that 5% rule and not use the quadratic equation when trying to find x.